Hey guys, welcome to today's video on titration. So here's a question that we often want to answer in our chemistry work. Question is, how can we determine the molarity of a solution? Well, you'll recall that molarity is defined as moles of solute per liter of solution. If you are the person who made the solution, then you would know how many grams of solute you used, use the periodic table to change that into moles, and then divide by the total liters of solution that you created. Sometimes, though, we're going to be given a solution and its molarity is not known. So we've talked about Beer's law, which is a relationship between how light is absorbed by a colored solution, how that relates to its concentration. So we said that if you have a spectrophotometer, you can shine a light through your colored solution and the absorbance is recorded, and then you use either a proportion method or a calibration curve to convert that absorbance into the corresponding molarity. Okay, today we're going to talk about yet another method, and it's known as titration. This is an experimental method in which you have a solution known as your analyte. And you know its identity, but you don't know how concentrated it is. So that's what you're analyzing. So let's suppose we have hydrochloric acid. We're going to measure its volume very carefully, and we're going to try to figure out what is the concentration of this hydrochloric acid. The second substance that's involved in a titration is the titrant. So this will be another solution, and it's a standardized solution. That simply means that you know its molarity very well. So we're going to say for today's purposes that this burette is filled with 0.175 molar sodium hydroxide. Now, this method is called a volumetric analysis. It involves very precise volume readings. So again, the analyte, whose identity you know, and we're trying to analyze its molarity, we're going to take a sample and record its very precise volume. Then we're going to add our standardized titrant, sodium hydroxide, put it in the burette and record the starting volume. Remember how funky burettes are with the 0 at the top and the 50 at the bottom? So this meniscus up toward the top, 12.60 milliliters. All right, now the process of titration involves you adding this titrant in very, very small increments just until the moles of sodium hydroxide that you've added are exactly the right amount to react with the moles of hydrochloric acid in your flask. Okay, now how do you know what is going to be the stoichiometrically equivalent amount or the exact amount? Well, you have to have a balanced equation. So here I've got sodium hydroxide plus hydrochloric acid. This reaction makes sodium chloride and water. This is my blown up picture, so we can see what's going to happen on the particle level. All right, so in my flask down below, I'm going to put the analyte. That's the hydrochloric acid. Now, guys, I can't see these particles. To me, this solution that I'm adding it looks like water. It's colorless, it's clear. I have no idea how many how many HCl molecules are in here. Meanwhile, in my burette, I'm going to load up the titrant. Now, this is sodium hydroxide solution, and I do know its molarity. By the way, this solution is also colorless and clear. So, for all I know, it looks like I'm adding water to water. I add the titrant into the burette, and again, I want to record that starting level on the burette. Now, because this is clear and colorless, and this is clear and colorless, my eyes are going to have a hard time knowing when I've added the right amount of these to react with however many of these I have. I need an indicator. So I put into my analyte maybe just 1 or 2 drops of an indicator. This one is called phenolphthalein, and it's a weak acid. Notice how it starts with H. And it's colorless, so it's going to just be hanging out here in the beaker. Okay, now let's watch. I open up the valve on the burette and I drop in just the tiniest bit of sodium hydroxide. Well, guess what happens? Hydroxide bumps into hydrogen and they form the molecule water. Meanwhile, the sodium is in there along with the chlorine. Do they form salt? No. Sodium compounds, remember, dissolve in water, so these are virtually invisible to us. Okay, I've added some sodium hydroxide, level comes down. I'm going to open up the burette and add a little bit more. So here comes a bit. When it hits the analyte, the hydrogen and the hydroxide find each other and form the molecule water. And I've made even a little more salt for my salt water. Now, all of the HCl at this point has been reacted. It's gone. But my eyes don't know that. So I open up the burette and I add again just the tiniest little bit. If you're good at this, you're adding a drop at a time. So in comes a drop of sodium hydroxide. These hydroxides don't have any hydrogens from HCl. They've all been consumed. But the hydroxide is going to hit this weak acid molecule. The H and the OH make water, and this leftover piece is actually pink. That's a visual clue. When you add that 1 more drop of sodium hydroxide and you get a pink color in your flask, that tells you to stop. So don't add any more. And instead, you're going to read the final volume on the burette. So we started here, we added sodium hydroxide, and we ended here. Okay, this faint pink color tells me I have reached what's called the equivalence point. And the equivalence point means however many moles of the analyte I have just successfully added that stoichiometrically equivalent moles of sodium hydroxide. In this particular titration, it's a 1-to-1. So however many moles of HCl I have now added that same number of moles of sodium hydroxide. Now be careful, some titrations won't be 1-to-1, but as long as you have a balanced equation, you can tell through the stoich step when you've added the correct amount. All right, so now let's talk about how we use all of this data to analyze the molarity of the HCl. Okay, so first of all, our starting volume of sodium hydroxide and our ending volume of sodium hydroxide. The difference between those two numbers, and I'm just going to put the big one on top for ease of subtracting. The difference between those two numbers is the volume of sodium hydroxide that I used. Okay, this is how much of the titrant was needed to completely react with the HCl. Now, I know something else about that sodium hydroxide. I know its molarity. And volume of that solution times its molarity will tell me how many moles I used. Okay, but let's make that a little clearer. You know how I've said in a problem, I don't want you to write molarity with capital M, but instead I want you to write it this way. And instead of using our volume of sodium hydroxide in milliliters, let's divide by 1,000 to change that into liters. Okay, so now I've got volume of my sodium hydroxide multiplied by the concentration in moles per liter. You see how liters divide out. If I stopped here, that would tell me how many moles of the titrant I used, but I'm really more interested in how many moles of the HCl were in the flask, so I'm going to apply my Stoich step. And in this particular reaction, it is a 1-to-1 mole-to-mole ratio. So moles of sodium hydroxide divide out. Now I'll get my calculator, multiply through, and my answer tells me this many moles. See how many sigdigs I took this out to. Titration is really precise work, so I'm not doing any rounding off yet. Okay, so this calculated answer is how many moles of HCl down here in the flask just got consumed by the sodium hydroxide. But I want to know molarity, and molarity is moles divided by liters. Okay, so these moles were in this sample. The sample occupied this many milliliters. Well, let's divide by 1,000 and change that into liters. Moles of HCl divided by liters of HCl gives me the molarity in moles per liter. I have just analyzed that this hydrochloric acid has a molarity of 0.104 molar. Okay, guys, this is a really useful technique and we'll do lots of practice with it. Hope that helped.